works at Mobiquity Inc. If you caught John Strand's talk, then he talked a lot about how people get into a lot of compliance, and that is exactly what I got into. But in my spare time, I do things like hack light bulbs. So going back to the very beginning, I just want to talk about college briefly, which is something that's very recent in my experience. A lot of my professors really kind of sold the IoT to new students. They were like, this is a really cool thing that you're really going to do a lot of cool stuff for. I had one professor who said, "Nah, I don't think that it's the next big thing." And the real reason why he said that is because he was my network security professor. Although it wasn't because he had strong feelings about IoT, it was just because he was not a very good professor. No need to, don't want to burn him super hard, but not the best class I had. So as a student, and even kind of currently, what did I know about IoT? Well, I knew it was that everything had access to the internet. Cool, let's address everything. I knew that my household appliances had the minds of their own. They could do whatever they sort of wanted to do. And I knew that I could turn on my oven from anywhere in the world. And by extension, anybody in the world could turn on my oven, which is not really a thing that I'm super jazzed on. But really, in reality, General Electric has an IPv6 addressable oven that you can preheat from anywhere in the world. So they actually want you to be able to do that. So does this sound like some sort of thing that you know about? Does it sound like some sort of ancient craft ringing bells? All right, well, if you're thinking demonology, then you're right, because that's totally demonology. Because household appliances can harbor external entities. They can have malicious intent. And this joke is not original. I got it from that article. Kind of a stolen joke, and this is clearly a transmutation circle. But yeah, I want to talk about light bulbs specifically as sort of an example of why IoT devices are really, really easy to break and really easy to exploit. So in the case of these light bulbs, just speaking generally about what you can do with them, you can do your own DIY haunting. You can turn on and off people's light bulbs and change the colors of their light bulbs from their network, and they will not know why it's happening. You can streamline your B&Es, turn off all the lights late at night, and just walk right in and take everything. And there are potential medical nightmares that come out of this. So obviously, I'm not condoning any of this. This is all bad. This is not the stuff that we want. And I'll talk more about medical nightmares that go along with this and who becomes liable in situations where these light bulbs are exploited. Yes, this is educational purposes only. Nobody here is streamlining their B&Es. Okay, so this all came because a friend of mine got these light bulbs and said, hey, you know a little bit about security. I'm like, I do know a little bit about security. Do you want to check out these light bulbs and see if there's something wrong with them? I was like, that sounds super cool. So as soon as I see an IoT device, I think, yeah, I kind of want to just nmap it and see what ports are running. I don't really know anything about it. I'm just going to black box this and see, oh yeah, what's it running? I use PN because I'm like, I know it's online. I set it up, put it all online, and I see that it's running port 9999. I want to stress this port because later we're going to talk about my conversation with TPLink. But yeah, port 9999 is open. So yeah, let's just use Wireshark and see what we can see on this device. Starting out, going through the use of Wireshark, I can see that it's sending stuff via UDP to the broadcast address. I'm kind of like, I don't really know what that is. There's data segments, but it's all going to the broadcast address. Kind of weird, but it's going to that port. I looked for that port. I used the filter to find what was going to that port, and everything is on the broadcast address, not on the address for the light bulbs, which I thought was kind of strange. But there were some observations that I could get initially from this. One of which was that the data segments that were kind of just garbled, they weren't of fixed length, which is interesting because that means they're probably not hashing it. Port 9999 is pretty much always used for communications to these devices from what I can understand, because that's what's really going to the broadcast address. And then I didn't have any traffic going to the light bulb directly, so I actually had a talk. So I thought there was something wrong with my wireless card. I did figure this out, probably, because I asked Larry about it, and yes, I think that it is just the wireless card that was the problem, but there was a circumvention of that I used a little bit later. I did cheat. I realized, hey, this is probably a problem with all of TP-Link's smart home products. So there's an article by Lubomir Strootman, don't want to mess that up, Tobias Esser for this website, Sofdesk Check and Company, where they do a lot of reverse engineering and all sorts of cool stuff to different IoT devices and other products. And they noted that the TP-Link smart plugs use AutoKey cipher. And that is a really, really weak cryptography scheme. They have a Python tool that they had available. It was sort of an older firmware version for the smart plugs, so it didn't quite work out of the box. Primarily the change is that now their smart devices communicate via UDP instead of TCP. It required just a little bit of tweaking, but I could get some of the old functions from their Python script to work with the Lightbulbs. So the command that I used specifically for the Lightbulbs was get sysinfo, which actually got a response from these Lightbulbs just running regularly on the network. And so that means that the encryption is actually the same between the devices. So I wanted to verify that. Here are two tools that you can use to sort of start getting into the reverse engineering of an application, because all of this is done from your phone or a product like Alexa through an API that they have that lets you basically just send all of this communication through their encryption scheme to the Lightbulb on the local network. So dex2jar is okay. It basically will take raw dex files, which are compiled Java, and they will turn it back into sort of readable mode. Sometimes it won't get all the class names. So it's not the best. Better, JADEX is really good. It's really versatile. It does a lot of different versions, a lot of different file types. And it's really readable. If there are file names and type names, you'll get all of those. It's really, really cool. I want to briefly mention that if you've got an NDK with compiled C code, you won't be able to read that. That's going to be actually assembly language. So you'll have to use some sort of ARM disassembler if you want to read that kind of thing. But in this case, there's nothing like that. It's all Java. Oops, didn't mean to do that. Can I get back in there with a button? Let's see. I'll just run over here. Okay, so why is it so easy to do all of this? Like, why is it really, really easy to decompile Java? The part of that answer is convenience. You want to be able to get this compiled Java onto a lot of different Android devices. So you don't want to assemble it. It's also because Dalvik, the type that you're going to use on Android, is a really, really readable bytecode format. So the process in compilation says, I'm going to turn Java into Java bytecodes, Dalvik bytecodes, and then I'm going to wrap that all in basically a renamed zip file. I'm just going to use an APK, put all that Dalvik in there. And the compilation doesn't happen until runtime. So you're never going to have assembly running until you're actually running the application itself. So the Zygote, which is the running executable, turns everything into optimized Android file type, which is the actual assembly language. So this is really, the culprit is really Java-C, which I thought was JVAC, but it is apparently Java-C for anybody who is a little bit bummed about that. The reason why this happens is because you look at a simple Java for loop, and then you look at the bytecode. You can see that there are, like, the for loops, the nested for loops are really obviously placed. It's not, there's no ambiguity here, right? You can see the inputs go in. You can see the go-tos down here. Same thing here. It's the same exact for loop. Like, you've got your inputs come in, you've got your go-tos, and then for your prints, you can see it, calling the static functions or like the library functions. You got your 1000 up there for the 1000. It's all very simple. It's not as complex as assembly. And because of that, it's really easy to programmatically turn this back into this. Yeah, so the overall process, you got your Java source. It runs through the Java C compiler. You get class files. Class files and jar files then go through a DEX compiler. You've got your classes.dex, and then you wrap all that stuff up with the resource files into an APK. So you can just you can rip open that APK, grab all those DEX files, grab all those resource files, and turn it back into readable Java, super duper easy. So companies will oftentimes use obfuscation on this kind of thing, which helps sometimes. It's a very dramatic looking demonstration of how ProGuard works. But in reality, when people use ProGuard, a lot of the times in their applications, it'll be in a really basic kind of way, and they'll want to leave a lot of stuff readable for various reasons. But pretty much the only thing you're going to see happen is, oh, this function is called A, or this function is called B, and I still have a lot of really clear variables in here. So here is me trying to match the cryptography that I saw the soft-s check guys do. I'm trying to see, oh, is this still in the application? And I want to talk about this little thing, this little trick that I keep forgetting about, which everybody should use this all the time if you're ever trying to look for anything in a lot of directories, because it is really, really helpful. And it's apparently, I mean, it's super obvious to some people. I'm not really a master of, of Bash, so it's a little bit, I have to write this down, put it on a sticky note on my computer to make sure that I'm not forgetting it. But all I did here was I used this, and instead of whatever, I looked for byte arrays, because I know they're using byte arrays for their cryptography methods. And I found it. So this is what the soft-s check guys had, a slightly different obfuscated name. Maybe they're using a different decompiler, but I found it as B. They also had another cryptographic function, which was A. Slightly different. You'll see that a lot of the code here is the same. I'm going to run through these. It's really basic crypto, so if you know crypto, this part's going to be like, ah, this is boring. I already know this. But if you don't, hopefully you learn something a little interesting. Let's see. Yeah, so B, the function that they have there that they actually use for all of their encryption, is auto key cipher. If you've ever seen this, basically what you're doing is you're just taking an IV, and then you're pinning on everything from the plaintext onto the key, and then you're just XORing it. So we know that we have an IV. We can see that in the source code. We can see that it's 1 byte. It's -85, which is really moduloed to 171. Don't know why they used a negative number. And the remaining characters are tacked onto the IV. So I'm going to run through real quick just the really sort of simplistic methods that they were using. So if we want to encrypt hello using A, a function that apparently is never used with the IV 171, first we're going to run through and we're going to XOR that. Then we move that up. Then we XOR it again, move it up, XOR it, move it up, XOR it, move it up, XOR it. And the reason why they probably didn't use this one is because it's somehow even worse than AutoKey cipher, because you can see that we've got key material in the ciphertext. So you could actually just try to XOR the ciphertext with itself, and you would get back the actual key result. So you could get back the plaintext just by XORing the ciphertext with itself. So B is slightly better, and I really want to emphasize slightly because it's really only a little bit better. So what they do here is they're setting the ciphertext or the key to be the plaintext from the previous byte. So, you've got all the plaintext bytes moving forward into the key, and then you XOR everything. So you no longer have that issue that you had where you can see the key in the ciphertext. There is still another problem, and that problem is this is really only 1 byte. You can brute force, if you know this is ASCII or UTF-8 or whatever, you can brute force these byte codes. You can just say, I'm going to go 0 to 255, whatever, and I'm going to see XORing with an IV if I can get back the plaintext. And if you can decompile, you know what the IV is. And it's arbitrary to decompile. So you can really, really easily get this result anyway. So I couldn't get any Wireshark traffic from my machine, but I decided, well, I can maybe use the app itself. I can maybe actually use my phone to do this. So I tried to look at the syscalls that I was sending to the broadcast address. Figured that's probably what's populating the dashboard for the app. That's what's being sent via UDP, and it's sent to the broadcast port 9999. And then I decided, yeah, I want to figure out a little bit more, so I'll use NetHunter, and I'll just TCP dump off my phone. So I did this on a Verizon phone on an S5, and Verizon really likes to lock their recovery partition, which is really annoying. So if you want to CH root your phone, better to do it on a non-Verizon phone. But yeah, the Kali CH root NetHunter is really, really good. It's got a lot of tools built in, like Csploit and all sorts of other cool mobile app reverse engineering things. And of course, you've got TCP dump, which is really what I needed in this situation. TCP dump, it's just going to give you the same kinds of files that you would get from Wireshark, just in a very hard to read way that you can then put back into Wireshark if you're lazy like I am. So I did that. And here I'm seeing a lot of stuff to the broadcast address, but I'm also seeing other stuff to port 999 that's not on the broadcast address now. And I'm seeing a lot longer signals. So the get sysinfo actually has another component when it's being sent from the phone and being sent directly to the light bulbs. All this crap here is just a bytecode representation, which not very important, but kind of interesting. And again, here is a really curious part about the setup that I actually just did with these light bulbs here. Not as big of a deal in an open network like we're in, but they generate their own network during the setup process. You say, oh yeah, I want to connect to this light bulb so that I can tell it my network's SSID and password, right? Well, their network for the light bulb doesn't require any authentication. So it will send, encrypted in the same format, your password and your SSID for the network that you want it to connect to. And I noticed while I was setting these up today, oh yeah, my phone automatically connects to all TP-Link light bulbs now. So you could just sit around waiting for somebody to set up their TP-Link light bulb and get their Wi-Fi password. Yeah, so I mean, you've got to put that in, and that's really the only way to do it. This is a really common methodology. Alexa does the same thing, but Alexa uses SSL, an SSL server. There are still practical attacks that you might be able to pull off here. They always have the same name again, so you might be able to do some sort of evil twin attack with an HTTPS server. You would likely have to be able to reverse engineer the firmware, pull out whatever certificate they use. But it might be possible, and it's relatively new hardware. So this is a kind of technique that is really becoming prominent with IoT devices. So anyway, yeah, I went looking for a little bit more stuff. Here was the newly set up network that I was using when I was doing TCP dump. Seeing really, really long data segments here, just running those through my translator. I saw that there was a get light state, and that was cool because that means I'm getting the exact, is the light on? What color is the light? How bright is the light? So I said, oh yeah, I'll just run set. That'll be really easy, no problem. In reality, it was not set. Annoyingly, these light bulbs use a different nomenclature for changing the state of the light, and that is transition light state. So I guess they did that because they wanted to mask the fact that they had really, really bad crypto. So maybe for reversing it, you're going to stop here and you're going to say, it's not set light state. I guess I can't look for any functions. I guess I'm done. But you can now, pretty much, once you know that transition light state is the JSON that you need to do, you can just send it commands from your computer. You can turn it on and off. So it's really no problem. It's super duper arbitrary to swap somebody's lights from on to off, swap them from bright to dim. It's really no problem at all. There's a lot of other really interesting stuff that the TP-Link smart home devices do. One of these things is there's a command in JSON that you can send to it to download firmware from any URL. That's cool. You can check the download state of the firmware to see how far along the process of downloading you are. Am I done? Cool. And you can flash the firmware that you've downloaded. Great. This is from the smart plug. Again, this is from SoftScheck. I haven't gone through the process of actually physically reverse engineering the light bulbs, but in the smart plugs, they actually check the hash of the firmware. So maybe a little bit of a layer of security there. Weirdly, they accept multiple hashes, probably for debug or rooted versions of the firmware. So maybe if you can get your hands on that firmware, or maybe if you can match a hash of one of these firmwares, you could do some interesting things. Not sure if the light bulbs do that. I suspect they probably do, but it's possible they don't check the hash. So if anybody out there wants to make some rooted firmware for TP-Link LB120s, go for it. It would be really cool. I'd like to see that. So I told TP-Link, I called TP-Link, and I said, hey guys, I'm just going to let you know that your devices, your smart home devices, can all be connected to and arbitrarily turned on and off and modified in many different ways. And the guy was like, oh, cool, I'm sitting right next to our engineers right now. I'm going to tell them, and they're going to get right on it. I'm like, cool. And he's like, no, we'll email you. So this is the response I got back from their email. We received an update from our VIP support team requesting issues you reported regarding port 99. They have advised they are working on enhancing the communication protocol for our app. There was not much more information they could give us at this time beyond this. Thank you. So I think that they're going to fix it right away, probably. So what are the implications of this? It's dangerous. That's what I know. In essence, the real problem here is that these light bulbs can be flashed pretty fast. And demonstrated in Paris was Philips Hue light bulbs being hacked to flash really fast via the Mirai botnet all across the city. So you can definitely get into some weird medical territory here. People can definitely get actually injured. And then what happens? Well, the people who have bought the light bulbs are probably the ones who are liable in this situation. So if you're going to be putting this light bulb in any sort of place where you're having people that are not you residing, you're in danger because somebody could come in, make somebody induce a seizure, and then, great, I got to pay the medical bills, and maybe this person died. That's great on my conscience. And if this is going beyond, just the TP-Link bulbs, we're talking about like, what if this person isn't even the owner of this stove that they're trying to turn on? They're preheating. There are a lot of devices out there that have a lot of power over our homes and a lot of power over businesses and a lot of power over all sorts of things. We want to make sure that if we're going to be using something like that, this in our lives, that it's secure. And right now, a lot of them aren't. So you can try yourself. This is clearly me. Yeah, just grab yourself an LB120. You can download the script from my GitHub, hachisanju dumb bulb. You can try it on this light bulb if you want to connect to the guest network right now. But yeah, it's kind of fun stuff. Definitely give it a try, and that's pretty much all I got right now. I mean, if you guys have questions, I would love to answer them, hopefully, if I can. Yes?
Would the same thing be able to be done with the refrigerators or the washing machine?
It really depends. I mean, if people who are making these things decided to just use a garbage encryption mechanism for the local network, then yeah. The cocktail that made this possible with the light bulbs is that they were set up on a local network. The local network only uses very loose encryption, and it's really easy to break that. So it depends on what company you're going with. Oh yes, sorry, yes. The question was if this can be repeated on, if this kind of attack can be done on washing machines or refrigerators or any IoT devices like that. Yes.
I guess the reason why the encryption is so low is because like light bulbs are so
Right. So the assumption is maybe this is because this is a product that's distributed widely internationally, and we want to keep a very simple mechanism for situations where we're putting these all over the world. I mean, it's definitely possible. I don't know why they decided to do it this way, but they did. Yes. Could you what? Yeah, so if you can access, the question is, can you pivot to other devices on the network? If you can access this, you can send it that download firmware command. If you want to get your own rootkit for these Lightbulbs set up, you can root this Lightbulb, and then you can run anything that you can run on whatever architecture it's running, and you can do some wacky stuff, I'm sure. You probably could get persistence on a Lightbulb if you can do some cool firmware hacking. Anything else? All right, well, if you want to mess around with it, come up here. But yeah, thanks, everyone.